Hello, this is the second video in my series about oscillators, and today we will be talking about the Astable Multivibrator. So in my previous videos, we talked about the fundamentals of oscillators, what kind of things oscillate, what is an oscillator, and what are the key features of an oscillator. So oscillating is to go back and forth between two states, and an oscillator is something that does that without damping. In other words, an oscillator will have some kind of a mechanism to kick in more energy into the oscillating object so that it doesn't damp out and eventually stop oscillating. And the key parameters of oscillators are amplification, positive feedback, where we have our feedback coming back in phase with the input. So we have our output going back to the input in phase so that the output adds energy to the oscillator. And then we have a time delay, which is going to determine the speed of the oscillation and is also going to provide our positive feedback. And we have a time delay which determines the frequency of the oscillation and also is part of our positive feedback. And then if we want a sine wave oscillator, we do have to have some negative feedback so that the oscillator doesn't saturate and therefore produce square waves or otherwise produce unwanted harmonic frequencies. And we also talked about how acoustic feedback causes oscillations in an auditorium or other types of PA systems, and we related that to the electronic oscillator known as the phase shift oscillator, which works pretty much the same way. Today we are going to talk about the Astable Multivibrator. So let's start out with the amplifier and work our way up to the Astable Multivibrator. So when I started preparing to make this video, I started thinking about oscillator circuits and what the parameters were, and one thing I thought of was a simple common emitter amplifier which satisfies the need for amplification, and I'll make this about as simple as I can make it. Let's power this by positive 10 volts and have our bias resistor here. There is our input, there is our output, and careful biasing can make this a working amplifier. And what do we know about this? Well, if we have a signal coming into the base, let's say we have a simple sine wave coming in. So we have a sine wave input caused by an oscillator somewhere else, and that is going to have a voltage that goes up and goes down and back up in a cyclic manner. And remember that at the collector of the common emitter amplifier, we have a current coming through the collector resistor, and as that current increases, we get more voltage across this resistor. And we call that a voltage drop, and that's appropriate for this situation because as we get more and more voltage across here, we're going to get, let's say we get 10 volts here, let's say we have 1 volt across this resistor. As we know, that voltage will be highest where the current enters the resistance and lower where the current exits. So if we have 10 volts here and 1 volt across it, we're going to lose 1 volt. So we'll end up with plus 9 volts. And as that increases, let's say we go up to 2 volts, we increased our current, our voltage went up to 2 volts, so now we start with 10, we lose 2, so now we have 8 volts. So as this current increases, this voltage goes down. So as our base current goes up, our collector voltage comes down. So we look at our base voltage again. Voltage goes up, voltage goes down, and so here our voltage will go down and back up. And then as this voltage goes down and back up, this voltage will go up and back down. So we have a 180-degree phase shift from the base to the emitter of the common collector amplifier. So what's going to happen if we feed that back into our input? So there's our 180 degrees out of phase voltage here. We're going to take that out, feed it back to the input, and that's going to be phased like that. So when this is going up, that's going down, so that's going to be trying to push that down. And as this goes down, the voltage coming back is going to try to push that up. That's negative feedback. So how can we turn that into positive feedback? Well, we briefly talked about the phase shift oscillator, where we have a time delay circuit at the input, and we used 3 capacitors and 3 resistors and take that back to the output. And so we designed this so that the time delay at the frequency we wanted this to oscillate was such that we got our input. I'll put that right here. Here's our output, but the time delay caused our output to be late. Now when this is going down, that's helping push it down. And if we continue, when this is going up, that's helping push it up. So now we have that positive feedback. So that was the phase shift oscillator, but is there another way we can get our positive feedback? Well, what's our problem here? We have a 180-degree phase shift from our signal in to our signal out. What if we put another common emitter amplifier here? And we'll just ground that right there and send this back to the input. Well, that's going to be, goes up and down and back up, goes down and up and back down. That's going to give us another 180-degree phase shift. And so if we feed that back in, will that oscillate? Probably not, because except for a parasitic capacitance, we don't have any capacitance to cause a time delay, and so there's nothing to time the circuit. Although that could happen at very high frequencies, these transistors probably can't handle it, so I doubt this is going to oscillate. But let's put some time delay in there by putting in some coupling capacitors. Simply putting those in will give us some time delay. So put one here and one here, and now we have to put another resistor in here to bias that. Now, will this oscillate? Don't need this anymore because we don't have the phase shift circuit. Will that oscillate? Well, yes it will, because what I have drawn is an astable multivibrator here. These capacitors give us our time delay that we need to get this to actually oscillate, and we do have that 180-degree phase shift. So these capacitors will add the time delay that will cause this to oscillate, and we also have the positive feedback, so this will oscillate. Now the astable multivibrator is usually drawn a little differently, like this, but this is exactly the same circuit. So how does the circuit work exactly? I explained it in detail in another video in an answer to a question, and I went into quite some detail, moment by moment, looking at how this works. I'm going to give that same explanation, but I'm going to simplify it. So if you want to see how this works in much more detail and without me doing any hand waving for some things that really don't matter but are perhaps interesting and important in some contexts, you can go take a look at that video, and I have a link in the description below. So let's take a look at how this works, and I'm going to draw the typical way we look at the astable multivibrator. So we'll start with one transistor here, and our other transistor right about here. And here's our collector resistors. And there's the capacitors. Crossing over to the bases. Emitters are grounded. And here's the bias resistors going to the two transistors. These are all plus 10 volts. And just remember what this means is that somewhere there's a battery that's tied to our plus side is going to all of those plus 10 volts, and the ground is going to the other side. So this is a 10 volt battery. So just remember, we're just eliminating the clutter of having a battery on here. Let's get that out of the way now. So here's the circuit ready to go. So we're going to power it up, and what's going to happen? Well, if these transistors were perfect and the resistors were perfect and the capacitors were perfect, nothing would happen. It would just sit at some steady state. I'm not sure exactly where it would be, but of course that can't happen because These two transistors won't be perfectly the same. Even if they're from the same batch, they're not going to be perfect. The capacitors are not going to be exactly the same. The resistors won't be exactly what they're labeled. And so one of these transistors is going to get more base current than the other, and one's going to cause more collector current than the other, regardless of the base currents being different. And so one of these is going to want to conduct more than the others. And it's going to very quickly put us into the situation I'm going to put us at right now, which, let's just say at this point this transistor is turned on. So we have a large amount of current flowing through there. It's basically a closed switch. So if we have a closed switch, how much voltage difference is there going to be between here and here? Well, if it's a closed switch, it's a short circuit, we're going to have 0 volts. And at this point, the other transistor is going to be exactly the opposite. It's going to be turned off. So it's going to look like an open switch. So there's going to be no current flowing through this resistor. So this collector will be 10 volts. And so therefore, the voltage here is going to be about 0.7 volts. Of course, these are positive voltages. And this one's going to be off, so it's going to be basically 0 volts. Now, this is going to be maybe 0.4 of a volt, but I'm going to round down or up as necessary just to simplify the circuit. It'll work regardless. Now, what's going to happen? At this point here, we have 0 volts there. There's 0 volts here, but that's not being held to 0 volts. It's just where it happens to be at the moment. It's going to take a few seconds to get to this particular state. So if we turn this on, we watch it on an oscilloscope, we're probably going to see a little bit of some transients, and then it's going to go to this state, but then it's going to start doing exactly what I'm going to describe here. So what's going to happen is this capacitor is going to charge through this resistor. So we're going to have current flowing that way. Of course, at the moment I turn this on, this capacitor is going to be uncharged, so it's going to look like a short circuit. Remember, when we first start charging a capacitor, let me draw our little sample circuit here that we use to explain capacitors. My example circuit. Let's assume that this is completely discharged. So at some point I had another switch here. Close that switch to completely discharge that capacitor. So it's completely discharged, and we're just going to get rid of that. Capacitor is completely discharged. We close this switch, and current's going to flow. And at that moment I close that switch, this capacitor will look like a short circuit. But as it charges, it will collect more and more voltage, so it'll start looking like a variable resistor that's getting higher and higher in resistance. And then eventually, let's say it's a 10-volt battery, eventually that's going to reach 10 volts. And at that point, it's going to look like an open circuit. But it'll also have a lot of energy contained in it because it stored up all that energy as it charged. So that's exactly what's going to happen up here. That's going to charge up. And when that gets up to 0.7 volts, that 0.7, well, let's go a little lower than that, 0.6, just because 0.7 is going to be what we have here when it's fully saturated. I'm just trying to be a little realistic here. When that gets to about 0.6 of a volt, this transistor is going to start turning on. And so now we're going to have current flowing through here. What's that going to do? This transistor is turning on, so it basically becomes a short circuit. So we're going to get a lot of current flowing through this transistor. And because it looks like a closed switch, for two reasons, we'll see 0 volts here. The other one is, if we have enough current through this resistor is going to cause a voltage drop. The more current, the more voltage. Well, when we get to 10 volts across there, start with 10, lose 10, we have 0 left over. So two ways to look at why that has 0 volts. One, this is a closed switch, so it looks like a short circuit, and the other one is because of the current through the resistor. So now this is at 0 volts, and this capacitor was not charged to begin with, and so it's going to pull, and so since there's no charge on this capacitor, there's no voltage across there, therefore the voltage here is the same as the voltage there, so this becomes 0 volts. So that's going to pull this down to 0 volts. And of course what's going to happen, that's going to turn off this transistor, that's going to go to plus 10 volts, and so now we've just completely reversed what we had before. So now this capacitor is going to start charging, and when it charges up to 0.7 volts here, it's going to flip this transistor on, which is going to pull that voltage down, which is going to pull this voltage down flip this one off, that voltage will go back up. So it's going to go back and forth, 10 volts, 0 volts, 10 volts, 0 volts, back and forth and back and forth. Now, like I said, I do have another video where I explain this in more detail and show some nuances that aren't really necessary to have a basic understanding of this, but to have a fuller understanding, you might want to watch that video. But I just want to go over the basics in these videos. So we see that this is going to go back and forth. That's one way to explain the Astable Multivibrator, is how these capacitors charge alternately and keep turning those transistors on and off. And of course, they're going from saturation to cutoff, saturation to cutoff. And so what's our wave shape going to look like? 10 volts, 0 volts, 10 volts, 0 volts, 10 volts, 0 volts. We're going to get a square wave. There's a little bit of a fudge factor in there because of the time it takes to charge the capacitors. So if we take a close look, it's going to have a slightly rounded leading edge. And so there's our 10 volts and 0 volts. So it's not a perfect square wave, but we can send this through a Schmitt trigger, which is something we'll talk about in digital circuits, but a circuit that will clean that up and make it a perfect square wave if we need a perfect square wave. If we don't need a perfect square wave, then it'll do well enough. Now let's look at the other way to look at this. May or may not be a more simple way to look at the Astable Multivibrator, and that's the way we first did. So there's our transistor number 1, go through a capacitor to transistor number 2, collector resistor, bias resistor, collector resistor, bias resistor, and our obligatory plus 10 volts in each one of these. Each of these goes to ground. And we'll put our other capacitor there and bring this back to get our feedback. Now we're looking at this as two amplifiers instead of the cross-connected transistors, but it's exactly the same circuit and will work exactly the same way, but I'm not going to explain it that way because I redrew it to explain it a different way, which we already did sort of, but I'll just reiterate it. So what we have now is a circuit where if we have a sine wave here, it goes up and down and back up. We're going to have a 180-degree inversion here. And so what we need to do is invert that again. So we're going to go through the second stage. So now we get positive feedback because when this is going up, that is going up. So that's going to give us our positive feedback and make this work. And also the capacitors and resistors will give us a suitable time delay to make the circuit work. But because we have very high gain, we're just going to saturate every cycle. So instead of getting a sine wave, it's going to get a big sine wave. I'm going to draw it really big here because what's going to happen is it's going to hit the voltage rails because it can't go below 0 volts, can't go above 10 volts. So there's plus 10 volts, there's 0 volts. Clean that up a little bit here. So draw the connections. And so swing up, down, up, down, up, down. It just has too much gain. And so we are not going to get a sine wave out of it, but instead we will get this square wave. And this is called a multivibrator because, as we talked about before, if we have a sine wave, we have one frequency. If we have any other wave shape, we are mixing other frequencies in there, usually harmonics of the base frequency. And here we have the base frequency plus all of the odd harmonics in phase with decreasing amplitude for each harmonic. So we can build up a square wave with a Fourier synthesizer where we can add frequencies together, or we can make a square wave by just switching something on and off, which is what these do. So if we look at the collector of this transistor, we're going to get that square wave. But what are we going to see if we look at the collector of this transistor? Well, when this transistor's on, this one's off. When this one's off, this one's on. So they're going to be exactly the opposite. So one transistor's on, the other one's off at the same times, and we get these two complementary outputs from the two collectors of these transistors. So we have what we need. We have amplification. We have feedback. It's positive feedback because of the flipping of the phases. We get our time delay because of the time it takes to charge these capacitors, so it takes time for that to happen. But we don't have any negative feedback, so we don't have the stability we need to make a sine wave generator. Now, one thing you may have noticed is conspicuously missing from what I've been talking about is exactly what components we use and how to calculate what components to use for this oscillator. And you've probably found the same kind of lack in almost any place you've looked at how oscillators work. Well, there are formulas we can use to calculate these resistors, but engineers are not going to do that because they're lazy. What we do is we find manuals that tell us how to design these things and where someone else has done most of that work. And so we can find a chart that tells us what resistors to use. Here's a quick look at what one looks like, but that tells us if you want a certain frequency, if you want to use a certain capacitor, here's the resistor you would use. The collector resistor isn't critical. 1K is typically used, but you might have to experiment with that to get it to operate. But if you want a 1 kilohertz oscillator, 1K will work quite well. And then the resistors you use for the timing part of the circuit, you can look up in a chart and decide which capacitor and resistor combination you want to use. And here's a circuit with components that you should be able to make work and would make about a 1.5 kilohertz oscillator. So that is the Astable Multivibrator. In our next video, we're going to take a look at a derivative of this, which is the Wien bridge oscillator. So if you want to help other people find these videos and learn electronics, you can give me a thumbs up down below and be sure to subscribe and hit the gray bell when you do so you get notified when I put up new videos. And if you want to learn electronics technology, perhaps become a certified electronics technician, or get a jump start in your studies in electrical engineering, you can go to Vocademy.net and take my free course. A big thank you to my patrons. I could not make these videos without your support, and thanks to everyone for watching.